In the last module, we connected our front end to our back end. We built the communication layer. But when you start building autonomous AI agents, you aren't just dealing with users clicking buttons anymore. You are dealing with programs making their own decisions and calling APIs entirely on their own. The security model completely changes. To understand this, I want you to imagine your backend system as a high security intelligence agency. In the old days, we built monolithic applications. The entire agency worked in one massive chaotic room. If a fire broke out in the translation department, the entire building burned down. Today, we use microservices. We split the agency into separate, highly secure, specialized departments. The way these departments interact and how they verify identity is what separates a toy AI project from a production-grade enterprise system. Let's break down the three pillars of this architecture. Pillar number 1, service decoupling. Instead of one massive application, you build independent services. You have an orchestrator service, a vector database service, and maybe a Python code execution service. The goal here is independence. If an AI agent writes a bad infinite loop and crashes the code execution service, your UI and your orchestrators stay online. But there is a massive trap here. It's called the distributed monolith. Imagine you separate your agency into departments, but every single decision requires 3 different departments to sign off in real time. If one person is at lunch, the whole agency stops working. If your microservices are so tightly coupled, the service A must wait for service B, which must wait for service C. You haven't decoupled anything. You just taken a monolith and added network latency. You fix this by defining strict boundaries and using asynchronous communication. Pillar number 2, the API gateway. Before anyone from the outside world can talk to any department inside our intelligence agency, they must pass through the front checkpoint. We use tools like Kong or AWS API Gateway for this. We never want the outside world to know the internal map of your services. The user just talks to the gateway, and the gateway handles 3 critical jobs. First, routing. The gateway looks at the prompt and says, this goes to AI chat microservice, and directs the traffic. Second, rate limiting. Imagine 10,000 people trying to storm the lobby at once. The gateway acts as a bouncer. It says only 50 requests per second allowed. This stops DDoS attacks, and more importantly, it stops users from bankrupting you with excessive OpenAI API costs. Third, request transformation. If the outside world speaks a different language, the gateway can modify the shape of the request or add tracking headers before passing it safely inside. Pillar number 3, machine-to-machine authentication. When a human logs in, they type a password. But what happens when an AI agent decides it needs to search your company's private billing database? Machines don't type passwords. They need M2M authentication. If your agent uses a tool, you have to prove its identity to ensure a malicious user hasn't hijacked the prompt to steal data. We do this in 2 ways. First, the OAuth 2 client credentials grant. Think of this as an automated VIP badge. The AI agent sends its hard-coded ID to an authorization server. The server replies with a temporary JSON Web Token or JWT. The agent attaches the JWT to its request. The database checks the signature, confirms it hasn't expired, and allows the search. Second, we have an mTLS or Mutual TLS. If JWTs are VIP badges, mTLS is a secure private underground tunnel between 2 departments. Normally, only your browser verifies the server. But with Mutual TLS, the server also verifies the client using cryptographic certificates. The internal microservice says, I will only accept data from a machine that holds the exact mathematical key pair assigned to my trusted AI agent. Let's put the whole picture together. 1. A user sends a prompt from the UI. 2. It hits the API gateway. The gateway verifies the user, checks the rate limit, and routes it. 3. The request reaches the agent orchestrator. 4. The orchestrator realizes it needs a tool. It uses M2M Authentication to prove its identity to the vector database. 5. Because the services are decoupled, if the database is slightly delayed, the orchestrator waits safely, handles the response, and streams it right back out through the gateway. This is how you design a secure decoupled AI backend. Now, we are moving from theory to practice. I'm going to show you the production grade code that makes the secure AI architecture actually work. First, how do we actually decouple services to avoid the distributed monolith trap? If your AI orchestrator tells the code execution service to run a heavy task, we cannot sit there waiting for the HTTP response. The orchestrator needs to fire the command and immediately move on. In FastAPI, we handle this using background tasks or message queue like Celery. Look at line 14. We are returning an HTTP 202 status code. This means accepted, not OK. Look at line 17. When the orchestrator hits the endpoint, FastAPI hands the heavy lifting to the background thread. And right there on line 20, it returns a response instantly. The orchestrator is free to keep streaming chat to the user, completely decoupled from the heavy processing happening in the background. If the worker crashes, the orchestrator survives. Next up, our front checkpoint, the API gateway. You usually don't write this in Python. You use a production gateway like Kong or AWS API gateway. We configure Kong using a simple YAML file. Let's look at how we set up routing and the bouncer rate limiting. This is declarative configuration. First, we define our internal service. Notice the URL. It's an internal IP address. The outside world cannot reach it directly. We tell Kong that any traffic hitting the /API/chat path should be safely routed inside. And here is the magic. The rate limiting plugin with 5 lines of configuration, Kong acts as a bouncer. If an IP address sends more than 50 requests a minute, Kong drops the connection right at the perimeter. Your expensive OpenAI billing account stays perfectly safe. Finally, the most complex piece, machine-to-machine authentication. How does our AI agent proves its identity when it talks to an internal tool? It needs a VIP badge, the JWT, and it needs a secure tunnel, mTLS. Let's look at the Python code for the AI agent making the secure request. We are using HTTPX here instead of the standard request library because it is fully asynchronous, which is mandatory for modern FastAPI. Look at line 7. Here is our VIP badge. We attach the temporary JSON web token to the authorization header. The receiving tool will verify the cryptographic signature of this token. But we don't stop there. Look at line 13. When we initialize the client, we are passing in cert equal to mTLS underscore certs. This is Mutual TLS. We are giving the client a public certificate and a private key. When it connects to the internal tool, the tool mathematically verifies that this request is actually coming from our trusted AI agent and not an attacker or on the internal network. So, background tasks for decoupling, Kong for the gateway checkpoint, JWS and mTLS for machine-to-machine security. Implement these patterns and your AI backend will be ready for the true enterprise traffic. Hope this is useful. See you in the next video.